Hello friends, I welcome you in lecture number 5 on curve fitting. In this lecture, we will discuss how to fit an exponential function of the form y equal to a times e raised to bx to the given data. In lecture number 4, we have seen fitting of power function y equal to a times x raised to b, and now we are going to discuss fitting of exponential function a times e raised to bx, and general exponential function can be written as a times b raised to x. So for fitting of any of these three types, what we are doing is we are taking logarithm to any base to both sides of these equations, and then we transform this curve to the straight line. That is, we take logarithm on both sides, and we find that the reduced form is the regression line, and we know how to find out regression line of one variable on another variable. So whenever you have fitting of power function y equal to x raised to b, or y equal to a times e raised to bx, that is exponential function, or y equal to a times b raised to x, which is general exponential function, what you have to remember is take logarithm on both sides of these functions, and then you will get regression line, and using that regression line you will be able to decide these unknown quantities in your exponential or power function. So here we are going to discuss one problem in which we will fit this exponential curve of the form y equal to a times e raised to bx. So let's discuss this problem, which is on fitting of exponential curve. This question was asked in GTU Winter 2020 exam for 7 marks. First we read what is this question about. The population denoted by small p of a small community on the outskirts of a city grows rapidly over a 20-year period. So here we are given some population of a small community on the outskirts of a city for different time periods. Here t is the time in years, that is time t, there is no year, 0 years, then time t is 5 years, 10 years, 15 years and 20 years, and the corresponding values of population are given. For t equal to 0, population is 100, for t equal to 5, population is 200, similarly for 10 it is 450, and for 15 and 20 we are given corresponding values of population. As an engineer working for a utility company, you must forecast the population 5 years into the future in order to anticipate the demand for power. That means you are given the data of population over a period of 20 years, and using this data you have to forecast the population 5 years into the future. So if we add 5 to this last period, we have 25 years. So if we can find out population corresponding to the value t equal to 25, then we can say that we have forecasted the population 5 years into the future. So for that you have to employ an exponential model and linear regression to make this prediction. So in short, we are given values of time t in years, and corresponding population values are given for t equal to 0 to 20 years, and using this data we have to predict the value of population corresponding to t equal to 25. So here I have written all these things in given problem. Small p is the dependent variable, t is the independent variable. We have to predict the value of population when t equal to 25 years, and here it is specified that employ an exponential model. So we can start with this curve y equal to a times e raised to b times t. here t is the independent variable, so we are using t instead of x. So this exponential model we will use and we will convert this into regression line. So suppose that here instead of y, dependent variable is p, so I have to write p as a function of t. P is an exponential function given by a times e raised to bt. So we start by assuming that small p equal to a times e raised to bt, and we have to determine the values of a and b in order to determine this function p, which is an exponential function of t. We have to determine the values of small a and small b. So first step is we take logarithm on both sides of this equation number 1, and we will consider natural logarithm. Taking natural logarithm on both sides of 1, we have ln p equal to ln of a times e raised to bt. Now here I can apply product rule for logarithm. We know that logarithm of product equal to sum of logarithms log m into n equal to log m plus log n. So here we consider m equal to a, n equal to e raised to bt, and we have log a plus log e raised to bt. Again we can use this property of logarithm, ln m raised to n equal to n times ln m. So I will have bt times ln e, and ln e is 1. So I obtain log p equal to log a plus bt. And now I assume that ln p is denoted by capital P, ln a is denoted by capital A, and I keep this as it is. So I have to write that capital P is ln small p and capital A is ln a. Now this equation number 2 is the regression line of p on t. So we can write down the normal equations for this regression line, and by solving normal equations we can obtain values of capital A and small b. But you can see in the given data we have these values of t are 0, 5, 10, 15, 20, and for normal equations we have to square these values and we have to multiply them with these population values also. So if we are going for these values of t and small p, our calculations will be large. We will have large numbers in the calculations. So one way is we can directly use these values of small t and small p, or what we can do is we can change this independent variable t to the new independent variable, say u, by some transformation. So we can change this variable t to the new variable u by this transformation. Here we can see there are 5 values for time are given. So this is the middle value. So we can write u equal to t minus middle value divided by this difference between successive values of t, which is 5. So I can consider change of origin and scale. I can define new independent variable u by t minus 10 divided by 5, so that t minus 10 will be equal to 5 times u and t will be equal to 5 times u plus 10. So we will not go for values of small t. Instead of that, we will change the variable from t to new variable u, which is given by u equal to t minus 10 divided by 5, and we will find out the regression line of capital P in terms of u. And after obtaining regression line in terms of p and u, we can put this value of t in that equation. So this is the idea, that we are not going directly for this regression line. Instead of this, we will change the variable t using this transformation, u equal to t minus 10 divided by 5. So I obtain 5 times u equal to t minus 10 Therefore t equal to 5 into u plus 10. So my variable t is converted in terms of u, and what I can do is I can put value of t in equation number 2, and I will convert my equation number 2 from p and t into p and u. So in the next step I am considering this t value, which is 5u plus 10, into equation number 2. So here I put t equal to 5u plus 10. So my equation is p equal to a plus bt, and here I put p equal to a plus b, and t is given by 5u plus 10. Now I simplify this, I multiply these two by b, and I obtain 5bu plus 10b. Therefore p equal to a plus 10b, which is constant, plus 5b times u. And now I can assume this a plus 10b equal to alpha and 5b equal to beta, and I find that regression line 2 is converted from p and t into capital P and u. So now I will try to determine these values of alpha and beta, because if I can determine alpha and beta, I can determine from these two equations, I can determine values of capital A and small b. So now we will use regression line of p on u, and for that we can write normal equations. Normal equations for this equation number 3 are sigma p equal to n times alpha plus beta times sigma u, and for second normal equation we multiply this by u, and we have alpha u plus beta u square. So we obtain sigma u times p equal to alpha times sigma u plus beta times sigma u square. Now observe that here you will require summation of u values, summation of u square values, and summation of u into p values. So we have to prepare the table for all these values, and this capital P is small ln p. So that also we can decide from the given values of this small p. From this small p we can decide capital P equal to ln p, and u will be equal to t minus 10 divided by 5. So accordingly I have to prepare the table. So here I have prepared the table. These are the values of t in first column, values of population. Capital P is natural logarithm of these small p values. So I have written all these values using scientific calculator. We can press this ln button for finding natural logarithm for each of these values. U is t minus 10 divided by 5. So here we have t values. So I start from this. If I take t equal to 10, I have 0. If I take t equal to 5, I have 5 minus 10 divided by 5, that is minus 1. For t equal to 0, I have minus 2. For t equal to 15, I have 15 minus 10, that is 5 by 5, 1. For t equal to 20, I have 20 minus 10, that is 10 divided by 5, which is 2. And if we add all these values, we have sigma u equal to 0. Then we require u square values. So minus 2 square is 4, minus 1 square is 1. Similarly, square of 1 and 2 are 1 and 4. And last column is product of u and p values. We have to multiply these two values. All of these values are multiplied and written in the last column. So from the table we obtain all these values. Sigma u is 0, sigma u square is 10, sigma u into p is 7.5496, sigma p is 30.4701. So now here I have normal equations, so I can substitute values of all these quantities in normal equations. First normal equation is sigma p. So sigma p is 30.4701 equal to b times sigma u plus n times alpha. Value of n is 5. So here I have 5 alpha equal to sigma p, because this quantity becomes 0. So if I use first normal equation, I will obtain this equation, and from this equation I can decide alpha. I divide this quantity by 5 and I obtain alpha equal to 6.094. Second equation is sigma u p equal to alpha times sigma u plus beta times sigma u square. Sigma u square is 10, so here I will obtain 10 times beta, and sigma u into p is 7.5496. So using that equation I find out beta equal to 0.7550. Once we obtain alpha and beta, we can decide small b and capital A. From equation number 5, small b equal to beta divided by 5, and now we have value of beta. So we divide value of beta 5 by 5 and we obtain small b equal to 0.151. And using this relationship, equation number 4, we obtain a equal to alpha minus 10 beta, and we have value of b and alpha. So a is alpha minus 10b, alpha is 6.094 minus 10, value of b is 0.151. So 6.094 minus 1.51, and we obtain capital A equal to 4.5840. Now capital A is log A, so from this I can write small a equal to e to the power capital A, and capital A is 4.5840. So here I have written capital A equal to ln A, and therefore a equal to e raised to 4.5840. That turns out to be 97.9052. So now we have values of small a and small b which we require in the equation number 1. Our assumption was a times e raised to bt. This we have given as number 1. So we substitute values of a and b here, and we find that this is not y, small p. We find that population is given by 97.9052 times e raised to 0.151 t. So this is the required exponential curve. Now using this curve, we can obtain value of population corresponding to t equal to 25. In the next step, we put t equal to 25, and we find that population is 4268.4228, and if we round off up to 0 decimal places, we have 4268. Therefore the population is 4268 when t equal to 25 years. So using this exponential curve fitting, we are able to decide the population after 5 years from the given period. We are given the population values over the period of 20 years, and we can predict value of population for t equal to 25. So this is very easy question. What we are doing here is we started by assuming that the functional relationship is exponential between population and time t, and we assume it as small p equal to a times e raised to bt. Now taking logarithm, we find out this line of capital P on t, and if we use this line then also it is fine, but to reduce our calculations, we are changing our variable from t to u by considering u equal to t minus 10 divided by 5. That is, we are considering change of origin and scale, and we find out value of t in terms of u, and we put that value of t in this equation in terms of u, and we obtain this regression line of p on u. So we write normal equations for this equation number 3, and solving normal equations we find out values of alpha and beta, and using these equations we are able to decide values of small b and small a. And because small values of capital A is log of small a, we can find out value of small a by taking e to the power capital A, and we are able to decide this exponential curve which is of best fit to the given data. And using this equation we are able to predict the population for t equal to 25 years. So this is all about this session. I hope you like it. Thank you.